on this computer. So, application layer in the OSI model deals with what is on your screen. So if you pull up a browser, that's the application layer. So HTTP, HTTPS, that stuff works at the application layer. So that's the OSI model. Just for the recording here, I went through all 7 layers real quick and kind of gave an overview of what each one is about. So next, we want to talk about data centers a little bit. So if you remember, we talked about hot aisle and cold aisle. This is kind of a little graphic representation of what a data center rack system looks like. So you've got a raised floor that the cold air flows across, and you want to put the cold air on the floor because cold air sinks and hot air rises. So you have the cold air underneath the floor and the hot air in a plenum above the ceiling. And so it makes a circulation motion here. So it comes from the floor up through holes in the floor into the front of the racks, and where it gets sucked in by the fans of the servers in each of the racks. So then the processors of the electronics on the inside of the servers then heats up the air, and it gets blown out the back, where it gets combined into this aisle here called a hot aisle, and then it flows up to the plenum of the ceiling, where it gets sucked into the air conditioners, or crack units they call it, which then gets pumped down into chilled and then pumped down to the bottom, where it is then recirculated into the server. So then the heat itself is then pumped outside of the system and ventilated basically with large heat exchangers, which is how an air conditioning system works. So this is called hot aisle, cold aisle, because we have aisles here on the front and the back for that are cold, and then we have an aisle in the middle called a hot aisle. And then there's various ways of isolating the air coming into the server racks and then blowing it out. So there's different chimney systems like this one here. They've got a big chimney amongst these rack groups here, and then they actually have doors to seal things off from the hot side so it doesn't mix in with the cold air coming through. So there's different systems for that. So that's for traditional data center design, cooling design. Another one that we had talked about, which was the chicken coop, which I thought was interesting and fun. Let's see if we can get a good picture of it here. Nope, we can't.
It's a literal chicken coop.
Yeah, exactly. That's what happens when you click Bing. Let's see if this works here. Can't really see it, but let me zoom in here. You can see it better. But basically, it is a they've taken the air conditioning out of it and just used cool air from outside, which then gets filtered on the outside of the building, and then giant fans push the air into the computer racks, which then go into the center of the building, which then the hot heated air rises up and then gets blown out at the top. So it's a way to save money, so you're not having to physically cool and use air conditioning to cool your data center. So in the northern climate, this would work wonderful. This would probably not be good for things like Arizona, where it's already very, very hot. But yeah, it's a really interesting design, and I just like the word chicken coop. So yeah, we talked about this earlier. So Let's see here. What else do we want to talk about? I'm going to talk about IP version 4 a bit. Let's see here where to go. But before that, I'm going to talk about DHCP, DNS, and pull up the slides on that real quick. Come on. For some reason, this computer is being very slow today. There it goes. All right, so we talked about DHCP, and this slide here kind of gives you the flavor of it, how it works. So your client computer, it comes, you know, by default with Windows, it has DHCP enabled. So what it will do is it will ask the nearest DHCP server using a broadcast. We're talking IP version 4 DHCP here. IP version 6 will use a multicast instead, but it use a broadcast, and a broadcast will go to all the other clients as well as every other server on that network, and then it will a DHCP server listens for broadcasts, and so it will then respond to the client saying, hey, I've got an offer, a DHCP offer. Here's the different packets. So you get a DHCP discover packet, which is your broadcast, and then the server broadcasts back a DHCP offer, and then finally the DHCP client says, yep, that's fine. I will have a request back to it, and then the DHCP acknowledges with an ACK packet saying, yep, we're set up. So then your client computers then have a DHCP address and can reach the whatever services they need to, such as different servers, DNS, internet, that type of thing. So, and that's basically how DHCP operates. Yeah, I don't think there's much more in these slides that we need to cover without going into too much detail with it. So yeah, that's pretty much it. DNS system. Actually, was it in that presentation? Might have been. I don't remember. Bring it back up here. Nope, that was it. So, okay, so anyways, so DNS. All right, so the way DNS works, this is a good picture here. Let's see if this actually works here. There we go. Okay, so let's bring this a little closer. So what happens is your client computer has a DNS server configured on it, and usually that'll happen with a DHCP request. It will come in through when it gives a DHCP address, it'll get a DNS server address as well. So when you type in, say, www.google.com, it will hit that DNS server first and say, hey, do you have google.com in your cache memory. And the DNS server says, well, no, I don't. Let's see if we can find that. So it will then go to the root server, which is .com, and so it knows about the root server of .com. So it says, hey, do you know google.com? And the root server says, yes, I do. It goes to this server over here. So then the DNS resolver goes back to the google.com server, and you have www. Yes, that's another server. And so then it goes over to the actual server itself, to www.google.com. So it gives it the address of it. So it's a multi-part recursive search, they call it, recursive query, and that's how the DNS system works. So anytime you have a dot, it's going to hit a different server to try to find which IP goes with that name. So it's the way DNS works. So that's pretty much all we need to cover in that one. We want to go over Ip4 addressing, though. That's really what we want to do. And subnetting and how that works. So in this sheet, it kind of goes over. Let me zoom in just a smidge. There we go. Okay, so with Ipv4 addressing, we have 2 to the 32 power, which is like 4.3 billion addresses. They're divided up into Class A, Class B, Class C, and Class D address ranges, of which we only use A, B, and C. Well, I take that back. D is used for multicast, but as far as our client computers and servers, we only use A, B, and C. D, the multicast, is mainly used for streaming services such as Netflix, or say video cameras, IP phones, that type of thing. So, anyway, so Class A networks are going to be in the 1 through 127 decimal range. So it'd be 1 dot and then a whole 0.0.0 would be your address range. Here we go, Class A. So these are private ranges, by the way, but the normal Class A range is 1 through 127 for the first octet. And then Class B is 128 through 191 for the first octet. And then also, it only uses the first 2 octets, though, is a Class B address. But the first decimal range here is where it begins at. And then same thing with Class C, except it's the first 3 octets are a Class C address. So you have, with Class C, you've got by default 254 addresses to play with. Class B, you've got 65,000, 65,534 addresses. And then with the Class A, you've got 16,770,214 max addresses with each one of those Class A addresses. So here in the private ranges, we have a Class A private range of 10.0.0.0 up to 255, 255, 255. And then Class B, 172.16, and Class C, 192.168. All of those are available for private use. They are not publicly routable on the internet. So these are good for your own personal, local area network, and then you could translate that to a internet routable address. And in fact, nowadays, because we're almost out of Ipv4 addresses, you have to use NAT if you're going to use Ipv4. So let's see here. So the type of notation that we can use instead of a subnet mask, which we don't really show here on here. So normal subnet mask.
That's the cider. So I don't know.
Yeah.
Right.
Well, it's, yeah. Oh, here we go. Here we go. The normal bits of the subnet mask, if you look on Windows or whatever, it's going to be a decimal notation. It's a 255.255.255.0 or any combination thereof of different subnets. This particular subnet mask is a Class C subnet mask. If you were to add up all the bits of each one of these octets, see these are 8 bits in each octet, so 8 times 3 is 24. So we would just write /24 to indicate that we're actually talking about a subnet mask of 255.255.255.0. So you have to have a subnet mask for every IP address in order to delineate between what is the network side of the address and what is the node side of the address. So by manipulating this mask, you can actually increase or decrease the number of nodes or networks depending on your needs. So especially when you're using these private address ranges, you have the complete range there to play with, so you can actually subnet it into smaller chunks as needed. So you can segment your network better. So anyway, so slash some number, usually a well, actually it is a 2-digit number. Even if you have like a 0, 1 or something like that, it would still be a 2-digit number. So it would be a CIDR notation, CIDR. Anywho, moving on. So this is just more information on how this all works with your IP headers and what bits and how many bits there are in each of the segments of the IP header, which we really didn't get into really good detail here on the class, at least during class, but on your own you can take a look at it. All right, so that's Ipv4. I haven't really talked about subnetting it though. So let's see if I can pull up some slides on that. I know, that's right. I made my own. Okay, because my handwriting is horrible, so Mark did this with on his whiteboard, and so I decided when I wanted to do subnets, I would just write it out in legible print. So we have here just an example of how to subnet your network. So say you have a network ID of 172.16.0.0 and you need to divide it into multiple subnets. So you need 600 host IDs for each subnet. Which subnet mask would you assign to allow for growth? So with these, I gave it multiple choice of 255, 255, 224, 240, 248, or 252. And in this case, answer D will give us 62 subnets with more than twice the amount of hosts required per subnet. So, well, almost twice, not more. But anyway, so 1,022 hosts would give us this with this subnet mask. These others would be appropriate as well, but wouldn't give you the number of hosts, the proper number of hosts. The closest number to that 600 that we're looking for. So that's the reason why you wouldn't go with these. Same thing with chat here. Oh, a website for my subnet. It's actually on Moodle, but here I'll bring it up real quick. All right, now I'm being made a liar here. Fine. So I think it is on Moodle because we have the Bitcricket calculator on there, which you can install on Windows, or you can use this web page called tunnelsup.com subnet-calculator, and it will pull this up, and so you can type in any address with a whatever subnet you want. Oops, too many. /23 instead of 24, and it would instantly give you all the different masks and CIDR notation and what your network address and broadcast address are for each one. So, all right. So, yeah, we covered we covered subnetting pretty deeply, but this is just kind of a quick review. If you remember how this all works. I want to say this is also on Moodle as well. So, anyways, we need to move on.
Yeah, we didn't really quiz on IP version 4. That was one quiz I didn't get to.
The subnetting.
We're gonna add that into the final here.
There it is. It's under February 8th through February 14th on Moodle, week 4. This is where the Bitcricket calculator and the online calculator were. All right, so moving on. We're going to talk about dynamic routing and dynamic routing protocols. So the best way to do that is to use packet tracer, I think. Let's pull it up here. Okay, so here we have, if you remember right, this is the packet tracer we used in class to describe the different routing protocols and how to set each of them up. But basically there's 4 different ones that you can do with packet tracer. One of them is RIP, the routing protocol, which has the ability to do 15 hops, so it's a basic routing protocol. Nothing, it's not really designed for massive networks with a 15 hop limitation to it. Whereas, say, EIGRP or OSPF, they don't have that limitation. And then BGP is the protocol of the internet. And so it can handle millions of routers. And so...
Which one can handle that many?
BGP, Border Gateway Protocol.
Okay.
So, yeah. And like I said, it's the language of the internet. So in this case, if you remember, we did the OSPF, and actually I did all 3 of them on here and how to set each one of them up. But basically, let's just look at the config real quick of this one. So here we are down at the router portion of the configuration on this router. This one is set up to a router OSPF3, which the 3 is just a process identifier. You can make it whatever number you want. Just make sure that when you're going to configure OSPF, you want to make sure you're always use the same number on this router so that you can have multiple instances of OSPF running if you need to. So that's the reason it's there for. Okay, so here we have two different commands. One's a network 10.0.0.0 with a wildcard mask of 0, 255, 255, 255. So basically, we're telling everybody, hey, I know about the 10.0.0.0 network here. And then area 0 means that with OSPF, you can divide your network into different areas. And so with OSPF, if you have an area 0 and an area 1, area 0 can't talk to area 1 unless there's a border router that will talk on both areas. So you have it configured for both. So you can segment your routing protocols even with OSPF this way. Same thing with, so the next one we have is 192.168 and also area 0. So basically we've made one area with all of these routers. We could have divided it up into 2 areas if we wanted to, but in this case, just to make things simple for time purposes, then that's the way we did it. So yeah, so the commands to do EIGRP are basically very similar. They just don't have the process ID to it, and you don't have the areas. Same thing with BGP, although BGP has a lot of different tweaks that you can do to make it perform faster, because by default it's very slow, but it also is a very, very powerful, because like I said, it handles all of the internet traffic out there. Now, the way routing protocols work is they have this table that it formulates by talking to the other routers. And if you do a show route or show IP route, excuse me, it will actually show you what is in its table. And it found all of these different routers in this here. So it knows about the different networks like 192.168, 100, 200, and 250. So it knows all about that, even though it's only physically connected on 3 ports. So it has communicated with the other routers to share routes for all the different IP addresses. And with Cisco, the ones marked C are directly connected. The ones marked O are OSPF routes that it's learned through OSPF. And if you look in the codes here, it shows you the different translations to these. So if you can do EIGRP, that's actually a D. S is for static, that type of thing. So, all right. So, any questions on routing protocols? Because that's pretty much what I got, without deep diving into it, because we need to move on, unless you need to get more. Actually, I need to keep that up. I do want to go over where to go. Yeah, this one. Ether channel types. So we have different types of ether channels, or NIC teaming, or port aggregation. You know, basically you're taking multiple interfaces on a switch or on a server and combining them to make it more bandwidth as well as redundant, so it's more reliable. In case, say, the NIC port on one of your servers goes out, or the NIC port on your switch goes out, you can actually have multiple switches and have the NICs lag. So if the switch goes out, you can actually have redundant links to it. So, and that's all done through these different Ether channel protocols. In this lab that we kind of did, this thing, we went over the 3 different protocols that you can do, well, 4 actually, for Ether channels, and that's LACP, PAGP, NIC teaming for Microsoft, and Ether channel, just straight up Ether channel. LACP is an automatic protocol. It's an open source, or it's a industry standard protocol, and it has an active port and a passive port. That's pretty much the I guess the flavor of it. So one side's got to be active, one side's be passive, and then it all works. PAGP is very similar, except it's Cisco proprietary, and it has an auto and a desirable side to it. So very similar to LACP, and in fact, I think Cisco worked on the specification for LACP, and then kind of made their own and made it more Cisco-ish. But they have to do auto and desirable because, of course, you can't do passive and active because, you got to name it different. So then Microsoft has their NIC teaming, which is incompatible with PAGP or LACP, but I believe also servers can do LACP, which is, like I said, industry standard. You can also just do straight up Ether channel, which I think is what the standard NIC teaming is now that I think about it. And with Ether channel, it's just set to on and on. That's it. You just turn it on. So, so yeah, that's pretty much the Ether channel types and how they're set up. Just real quick. We didn't really, on the exam, I don't think we got into the actual configurations of them much. So, all right, see what else we want to go over. Let's see here, VPN. Actually, VLANs is what I really want to talk about. All right, and then that's right. I forgot about that.
You're launching another version of Packet Tracer?
What's that now?
Oh, I thought you were launching another version of Packet Tracer.
Oh, no, I'm just launching a second instance of it. Although I think I've got it mixed up here. This is what I wanted. It's on my other screen. All right, so VLANs. Let's see here. So VLANs are a layer 2 technology. Remember, we have access ports and trunk ports. Access ports can be tagged with a numerical identifier, which would be the VLAN number. And those can be a 1 through 4093. Any number you want to pick in there, it doesn't really matter, as long as, obviously you keep track of which ones are which. And then trunk ports will transmit all VLAN identifiers across their links. And again, like I said, this is a layer 2 technology. So when you divide your access ports, when you put a different number on them, they cannot talk to each other. So the way you want to talk about this is if, say, for example, you have your network set up like this, where you have 3 different switches, and they all talk to one router, and the router has 3 separate interfaces, and you have 3 different groups of computers. Well, what happens if one of the groups wants to talk to one of the others, or wants to sit over in this area and it be attached to this switch? Is that possible? Well, with VLANs it is. When they're not VLAN switches, then it's not. So you have to add extra equipment in order to make that actually happen. So the way to figure this, think about this, the best way to think about it is to color the ports. So in this case, we have red ports attached to VLAN on VLAN 1. There it is. And then the blue ports are on VLAN 2. And then the orange port actually is a trunk port, and that will transmit both red ones and blue ones to the router. And the router is what actually will then route between the VLANs for you. So it actually will then allow communication between your different VLANs, which is in reality how it would work if you had different interfaces set up on different networks anyway. So it's kind of how that works with the router. It's just all in one wire rather than 2 interfaces. So then using this kind of gives you an idea of how you could set up your switches. Say you have different VLANs, engineering VLAN, marketing VLAN, accounting VLAN. You have it set up on 3 separate switches, and say this is all in one building here, and this is a separate building. Or actually, I take that back. This is all one building. So you have engineers, marketing, and accounting in one building. You have it the same setup in another building, and it all gets routed together with a router. So, and then we did a
Yeah, there's a, if you go back to that slide 4.
slide 4. Yep.
So with these red and blue, they cannot talk to each other at all. They're only PC C and D can talk to each other, and B and A can talk to each other. And if A wants to talk to D, they've got to go out to the router, and they get switched over to the other network and then back down. And so it literally isolates it with software and the circuitry. And remember Packet Tracer, when you created that switch? By default, we really didn't do much on the switch. All we did was we simply plugged everything into the switch and the switch into the router. And it's all in VLAN 1 by default. But if you had gone into the CLI on Packet Tracer with the switch, any of those switches, and put all your ports onto VLAN 2, and the connection was VLAN 1 up to the router, then nothing would talk out of your subnet to the router. You wouldn't have communication. So that literally, it literally isolates those. And so I just wanted to kind of clarify that or lock that in your thought process there.
Yep. And so when we talked about VLANs in the class, we used a packet tracer to kind of illustrate what that actually meant. And so we have a couple of different switches. One of them is your traditional layer 2 switch connected to the router, just like we had in that illustration. And we have different VLANs, VLAN 1, VLAN 103, and VLAN 104. Now, Cisco and other manufacturers for that matter, the default VLAN comes as VLAN 1, and then you add other ones to it. And then we have, on the other hand, a layer 3 switch, which combines the router and switch all in one. So this is actually this setup here, but it's all in one chunk right here. So the configuration is more. There's more configuration in this, but it's less devices. So you can actually have more functionality with your layer 3 switch than you do with a separated router and layer 2 switch. And then on this end, we have VLAN 1, VLAN 100, and VLAN 101. Now, you don't have to have the numbers be unique. So on this side, we can have VLAN 103 and VLAN 103. It just gets confusing. So that's the reason why I did it this way, is so that I could have my 192.168.103 match up to VLAN 103. But I could have had it just say VLAN 100 and had this IP address be different than this IP address, and it would have worked fine. So the VLAN numbers don't have anything to do with the IP address, but just for management purposes, it's a lot easier to, if you make them be significant somehow. So yeah, that's pretty much it as far as the how as far as the review goes. But take a look at the configuration real quick. So if you notice here, we've got interface port 2 has switch port access VLAN 103 and switch port mode access set up on it. Obviously, that's making that port an access port, and then you set it to VLAN 103. But these others, they don't have any configuration on them at all. And why is that? Well, actually, it does have a configuration on it. It's just the default configuration, which is switch port mode access and switch port access VLAN 1. So they are actually a VLAN 1 address on those, or VLAN, not address, but they're access ports for VLAN 1. So then we have switch port access VLAN 104. And then finally, for our uplink, we have it on gig 1 for our uplink, which is switch port mode trunk. And then if we wanted to manage the device, we could actually give an IP address to VLAN 1 and we could manage it. But this case, we didn't do that. So manage it remotely. With Packet Tracer, you can just double click it and get into the console port. So there's not a real big reason why you'd want to set up a management address on here. But in a real world situation, yeah, that's definitely a big thing. Setting up a management VLAN and putting management addresses on it. So that way you don't have to go to your switch physically to change the VLAN numbers on them, change the configuration. You can do it remotely using SSH or Telnet. And then I'll just show you this real quick. The difference is, so the interfaces are set up the same way with the switch port mode access and switch port access VLAN. But in here, where it says interface VLAN 1 and interface VLAN 100, interface VLAN 101, this is the routing part of it. So we have the IP addresses set up on all these individual VLANs, and so that way your VLANs then have an IP address associated with it, and the switch will automatically route between them all. And then, of course, you have to have, because it's a router, you've got to have a route of some sort in order to talk to other routers. You can do routing protocols. In this case, we did just a static route of anything 000.000 means anything going to 192.168.254.2, which is the other, this router here. So that way they could talk to each other. But yeah, that's pretty much VLANs and how they work. Just a real quick overview. And anybody needs to jump in with some questions, please feel free. Interrupt me. I'm here to help you guys learn and help you excel. So let's see here. Let's say all that, get all that. DNS, settings. But the only thing I haven't covered yet is VPN. Let's pull that up real quick. Okay, VPNs. VPNs are a secure way of sending data over an insecure network, say such as the internet. So you can have a remote user with a VPN client on their computer, and they can go from a insecure network such as a Wi-Fi, like a coffee shop or McDonald's or something like that, and you can VPN into a server at a branch office or a headquarters or a different server someplace else securely. So you can actually access data within these networks in an encrypted manner securely. That's one way of doing VPN. There's another way of doing VPN where you have a branch office or a large branch office, and they are connected to each other via what's called a nailed up VPN. And that's an always on VPN. It's basically the main headquarters has a branch office, and when you have the VPN set up, it appears as if this is just another part of the main headquarters. So it's on the same network setup as the main headquarters, even though it's on another part of the world. So anyway, so there's different types of site-to-sites VPNs, and you can use different protocols for them. The PPTP, L2TP, IKE version 2. IKE version 2 is the most secure, newest one. It's pretty much what everybody uses nowadays. PPTP is a point-to-point protocol. It's pretty insecure. It's been broken pretty good now. But we have L2TP and SSTP and IKE version 2. So these are a little more secure than PPTP was, and then IKE version 2 is the most. And I'm going to sneeze here in a second. So anyway, so there's different authentication. When you establish the VPN, this is the protocol to tunnel with. But in order to establish that tunnel, you have to use authentication methods, and there's different protocols for that. So you can do PAP or CHAP, MS CHAP version 2, or Ip. So MS CHAP version 2 is pretty good authentication, which is what most VPNs use. And then there's Ip, which is even more strongest security available for it. So, and then the other ones are older technologies, and they've been broken. So most people don't use CHAP or PAP anymore. So let's see here. These are all different slides. All right, so and then when you use a VPN client on your computer to access VPN remote over, to your work or whatever, that will be set up by your IT department at the main office. And like here at the university, We just have them go to a website, download the client, and attach to vpn.stmartin.edu, and they're able to access whatever they need to after that online. They have to, you can map drives, RDP into different servers or their own desktop in their office. But yeah, that's pretty much VPN. Do you have any questions or anything at all? Like I'm just talking to the Ethernet here.
Peter, I'm assuming that we already have all these slides already out there on Moodle that you just went through.
Yeah.
Okay.
Yeah, I'm not covering anything new.
Okay.
So we're just doing a review on for what the final exam is going to be.
Does everybody know what obfuscation is?
Obfuscation, like an OBF?
Yeah.
Okay.
Obfuscation. Do you know what it is?
Now you can't see me anymore?
Yeah, it hides. It hides, and that's what this VPN is doing, right? And so many of you, when you said, "What's my IP?" and you got done with the VPN project, and you went to what'smyip.com, and then it said your IP address is this, which was not your IP address. It was the IP address of your OpenVPN server. And so that was not the source IP address for all of your data, but it makes it look like that. And so then it thinks everything originates from your OpenVPN server, but the tunnel hides your actual location and your actual IP address so that they can't track you down. Even though they can't track you exactly where you're at, they can narrow it down to a specific provider or a region of the world. But that's one of the benefits of a VPN server. And some of you were like, this is not working. But then all of the traffic was not being forced through the tunnel. Once you forced all traffic through the tunnel, then of course you do what's my IP address, and it says, well, this is your IP address, right? So those settings in those config files of OpenVPN, hopefully those are, you're being reminded of the tunneling, the TCP ports that were used to create the tunnel, whether it's TCP or UDP, and what port you used. It's interesting that you can use both UDP or TCP, and then you can even change the port, 1194 or 443, depending. But those settings also determine if it routes or it tunnels all your traffic or some of your traffic, if it hides your IP address or if it doesn't hide your source IP address. But in the end, it's encrypting and tunneling that traffic between two sites.
Mark and Peter had a general question about the exam. Will there be any requirement to submit anything to any kind of submission required, or will all of the exam questions simply require a selection?
It's going to be a combination of multiple choice and an essay.
Yep.
So the essay
I'm sorry, go ahead, Mark.
Describe such and such, describe this or describe that. And then through Open Book, Open Note, you'll be able to just put in all the information that you've learned about it. And, I don't even care if you cut and paste this stuff into there. But probably the best sources of material are going to be the sources of material that are on our Moodle course, in the PowerPoints and in the documents that are listed in Moodle, because it should be all right there. You can go to the internet if you want, search there. But
well, without having to ask you guys to pin it to a number of keywords or phrases, would you happen to know the glossary or the number of terms that we might want to focus on for those types of essay questions? Because sometimes you'll see that there is a glossary along with the slides or source list. That may be giving the students too much, and I got to admit that if we're already familiar with the slides, then the glossary may be redundant, but I don't know if you already have anything like that in place.
So I had a question in the chat here about do you have to be on Zoom during the test? Yes, we'd like you to be on Zoom. We'd like your camera turned on, please. Just to make sure that everybody's there. They don't have somebody giving them all the answers over their shoulder. So,
Yeah, so video turned on. Yeah, and then when you say glossary, that's hard to nail down, Jonathan. But as you go down through, you've got the specific topics within the syllabus at the top of the little, or you've got within each segment each week. Where we're talking about, like we talked about OSI model, TCP, UDP.
Now, let me try to drill a little closer. It's like if you say, okay, describe a VPN, it's like, okay, you can't get away with just writing what the letters VPN mean. I mean, you're going to need to describe it. But in the description of VPN or any of the other kinds of abbreviations, there might, do you understand what the abbreviation is? So I'm just trying to make sure that I'm not overwriting something that may or may not be needed. Glossary is probably, as I said, probably won't be needed. So
yeah, that's a good point. What does the abbreviation stand for? If we just say, what are the advantages, disadvantages of using this or that, then it's just the specifics within the notes that you've got from Moodle and that you've taken as we lectured to just lay out the specific benefits, whether that's VPN or LACP or Ospf or DHCP. Right.
okay, thank you, Mark. I appreciate it.
but yeah, that's pretty much the different topics to cover. Just a quick overview of them. So yeah, if there's something specific you guys wanted me to talk about, I could. We got a few more minutes here, or I don't know. I can talk about something else if you like.
Will there be a requirement to do a packet tracer build of any kind? And if there is, okay.
No. Nope. Although you can do all the packet tracer builds you want, they're fun. I like them. So, but they're not required for the test.
Okay, thanks, Peter.
Oh! I'm looking through the Moodle here, and there's actually a topic that I forgot to talk about. So I do have a few minutes to talk about this one. So we talked about Ipv4, but we did not talk about Ipv6 real quick here. So the guys at the IEEE decided they needed more addresses because we were running out of Ipv4. So they decided instead of just doing 2 to 32 power or 2 to 33 or 2 to 36, now we're going to do 2 to the 128th, which gives us an undecillion amount of addresses, 340 undecillion to be somewhat precise. So some of the features though, because hey, we're going to come up with a new addressing scheme. Let's do some extras while we're in there. We're going to build in Ipv6, so the security is built into it. However, it is completely incompatible with Ipv4, so we're going to have our own DNS system, DNS version 6. You're going to have your own DHCP system, DHCP version 6. And same thing with ICMP version 6 as well. this is kind of how it's broken down. You've got the registry. You've got a network prefix of 64 bits and an interface ID of 64 bits. So it's divided equally in half between networks and interfaces. You do have some subnetting available of one of these 8-bit. I guess they're not really 8 bits.
They're double octets, 16 bit.
Double octet, that's what I'm trying to say, of subnets. So you've actually got 64,000 or 65,535 subnets per IP address network side, and then each one of those has 18 a whole bunch of addresses for whatever 2 to the 64th power is of individual IPs that you can do per subnet. So yeah, so you've got a lot of addresses to play with basically per subnet.
Quintillion. Quintillion.
What'd you say?
18 quintillion
18 quintillion, that's it.
per subnet.
God,
IP
a
addresses per
really
subnet.
big number.
Yeah.
So more than the actual internet has by quite a bit for every subnet.
And
So
then that subnet section of that IP6 address is in the last double octet of the network portion, the first 64 bits. And so the subnet's built into the IPv6 address, unlike IP version 4, right?
right. And so because they did this, this then allows them to have no subnet masks, needed. It's all built into the address itself. So that's one of the features, is there's no subnet masking. So however, instead of decimal digits, everything is a hexadecimal digit. And so instead of just 0 through 9 for digits, you've got now A, B, C, D, E, and F as well to signify 10, 11, 12, 13, 14, and 15. So as your digits, because hexadecimal is a 16-bit or 16-digit math way of writing numbers. Kind of like binary, except it's bigger. So that way it's actually makes things a little smaller than writing it in decimal or binary for that matter. And then there's 3 rules. You have 8 fields each written in hex of 16 bits each. You can remove your leading zeros. And then you have the 0 compression rule as well, where everything where all the zeros that are consecutive can be written with a double colon. And however, you can only do that once in one of them. And that way the computers can then expand that out and say, oh, that's all zeros, however many bits that is, it's all zeros. So then there's different special IPv6 addresses, similar to the special addresses in IPv4. There's a loopback address. So in IPv4, it's 127.0.0.1. Is your loopback address. Here it is .1/128. So 128 would mean that's the only address. So it's basically .1 is the actual address. And then the /128 is the CIDR notation for it. And then you have an unspecified address where it doesn't have anything, just a ... Default gateway address is ./0, which I'm not sure what the difference between that and an actual default gateway is on your router, but that's what it says. So, and then we have multicast addresses at FF02, or that's the all router multicast address for when you're doing SLAAC, SLAAC. And then we talked about SLAAC, SLAAC, which is stateless address auto configuration, which it allows you to not have a DHCP server, and you'll still be able to get a routable Ipv6 address with your computer just using the MAC address of your computer, and a multicast routing router, an all router multicast address set up on your router. So, and then we talked about how that happens, how we translated a MAC address to the EOI64 format, and basically you split the MAC address in half, then put FFE in between. Where did it go? It's in here somewhere. And then you flip the 7th bit. Now there it is. Yeah, FF:FE in the middle of your MAC address, and then you flip the 7th binary bit. Why you do that, I don't know, but that's the way it is, so that's how you do it. So anyway, so then you have built-in multicast. There are no broadcasts anymore. It's all multicast or unicast or anycast. And then there's different Ipv6 tunneling, which Mark already talked about just a few minutes ago in answer to a question where we had 6-4 or 6/4 or Teredo. All of these are different methods or different approaches to handling, translating, or tunneling Ipv6 over an Ipv4 network. So, and then this is a comparison between Ipv4 and Ipv6, just to give you an idea what the differences are. Oh, and I'm over time. So, if you guys have any other questions, otherwise we'll see you at the test. And just want to say it's been a pleasure doing a class with you guys, even though I haven't actually seen any of you, except for Jonathan. He turns his camera on every once in a while.
Yeah, it's been great. Thank you all for being part of this, and it's been a fun course. Hopefully, you've learned a lot about networking, and yeah. Hopefully you can take that with you and apply that into your software development. So you have that just that much more understanding of the network and the security and the functionality of how computers work around you. So thanks again.